Okay, good morning. What better way is there to start the day other than by geometric engineering? So we look forward to hearing more about this from Sakura.
Okay, well, thank you very much. Indeed, nothing better than constructing an ALE vibration at 9 o'clock in the morning. So let me start the lecture by giving you sort of a brief recap of where we were yesterday at the end of the lectures. And so, excuse me. So the recap is, well, I'm motivated that in M-theory, if you're looking at this local sort of singularity C2 mod gamma ADE, then you actually have a good chance of engineering something that's not a billion gauge degrees of freedom, at least some kind of Supergravity theory in 7 dimensions. And the gauge group is determined by the type of singularity. There are subgroups, finite subgroups of SU2, classified by ADE. And for the A case, I actually resolved these singularities for you so you can see these additional spheres popping out. And when you reduce M-theory, the 3 form along those, you get a billion gauge degrees of freedoms. And from M2 branes, you'll see the additional W bosons. And so overall, in the singular limit, you regain then a full adjoint for the gauge group of A or D or E type. So this was in 7 dimensions, and of course we're not interested in 7 dimensions. I was saying we should really be going down to 40, and that was interesting because there's sort of this class of geometries which are these G2 holonomy spaces. They're Ricci flat spaces, 7 manifolds, which are pretty tricky to construct in mathematics. And what we'd like to do here is just construct them from a purely gauge theoretic point of view. Yeah, so we start with the 70 Superyoung Mills, and then I proposed, well, let's sort of compactify that further on a 3 cycle. And the way we can do this is such that we actually can't just take a product because the product won't actually preserve supersymmetry, but if we suitably twist the R-symmetry of the 7-dimensional Superyoung Mills with the local Lorentz symmetry of M3, then we have a chance of getting a 40n equals 1 theory. And so we looked at that last time, so maybe I can dig out just this thing here. This was this twist. The twist for the supersymmetries was here, right? So this was this twisting of the 2 SU2s or SO3s. It's a Lie algebra, so it really doesn't matter, SO3 or SU2. And then we see the 2-1 and 1-2 singlets under this new twisted SU2, and that are our supersymmetries in 4 dimensions if we do everything correctly. And doing everything correctly means you actually have to solve for field configurations on the 3 manifold. And so the twisted fields were A, mu, phi, and lambda, gauge field, the scalars, and the fermions in 7 dimensions. Here I've already written down the twisted transformation rules under them in this light blue underlined way. And we see that the scalars and the gauge field components along the 3 manifold become 1 forms, right? The transformer 3, they have superpartners psi, and then there's the gauge field in 4 dimensions, A mu and chi alpha. Those are 0 forms on M3. And to actually find a supersymmetric theory in 4 dimensions, we have to solve the BPS equation, which means the SUSY variations for the vacuum expectation ones for these chi and psi fermions along the 3 manifold. And those are these equations in the green box. And where we were is that I sort of told you, well, what's a good strategy to start looking at these equations? So the BPS equations are written there again. And one insight that we had is, well, we need to be careful what we sort of wish for, because having compact M3 and pi 1 of M3, say trivial, say think M3 is a 3-sphere, phi is regular, this Higgs field, then actually there are no solutions. So really what we then decided on is let's consider the case where M3 is S3, where we have sort of taken out a charge distribution, right? So this problem, basically this solving for phi, sort of descended to a problem Laplace for f, where f is df is phi is 0, actually allowing for this to be singular, right? Essentially means we're introducing a source term there, so some charge configuration. And another way of, after the dust settles, the configuration that we decided was a good place to start this analysis is you have a three-manifold. Think it's M3 is S3 minus some tubular neighborhood of some charge distribution that's located on gamma, right? So this is this red and yellow kind of wires, if you like. Could also be point charges. We take out this tubular neighborhood from there. We get a manifold M3 with a boundary. And let's say M3 is this object with a boundary. The boundary is sigma, and that now has plus and minus charge contribution. Since it's a compact manifold, we're doing electrostatics on there, we really should be asking for this to actually have a charge conservation. So actually the integral, the sum of all these charges has to add up to 0, or the integral of the charge distribution has to be 0 over the 3 manifold. So this is the sort of geometric setup that we'll start with. What I didn't explain to you yesterday, and this is what I want to sort of dig in before we then start solving for the zero modes and the Yukawa couplings, is to actually ask, so what the heck does this have to do with an ADE vibration? You promised us, G2 is C2 mod gamma ADE over M3. Where does this come from when I'm looking at something like this, right? So like some phi solving these BPS equations. So I want to answer this question first, and then we'll dig in and actually try to solve these BPS equations and get to something interesting in terms of physics. So are there questions about sort of the things we talked about yesterday, or where we're going in the next couple of minutes? The metric, well, so here I'm doing a really bottom-up construction, right? Usually the metric is induced on a 3-cycle if you embed it, if it's in a G2. Here I'm really constructing it sort of, I start with M3 and I'm embedding it into the ALE vibrations. And I haven't talked about this yet, but we will get there. So the metric will in particular be important, for example, when you wrap brains on this and so on. I'm not sure, you're asking, can you actually construct a Ricci flat metric here? Well, we haven't even talked about this yet, so we'll get there in a second. How actually we construct the ALE vibration. So first thing is, so these ADE singularities, so C2 mod gamma ADE. We said they're locally, they're sort of like Calabi-Yau two-folds, or K3s, non-compact. But they're actually more than that. They're actually hyperkähler. What this means is, now basically the holonomy is SU2, but SU2 is the same as SP2 or SP1 in whatever notation you want to use, right? So this is, if you remember in this table, so the holonomy is SP2, so this is the case where you have a hyperkähler manifold, and they exist in 4 n dimensions. And in this case, sort of there's the generation that any Calabi-Yau two-fold is really also a K3 manifold. And what this means is there are now not just one complex structure, but there are 3 complex structures. So there exist 3 complex structures. So J, K, and L, or J, K, I, J, and K is usually the notation, so let me stick to that. And associated Kähler forms omega I equals to 1, 2, and 3. And for the C2 mod gamma, we can construct them very simply. So for C2 mod gamma, ADE, these are very simple to construct. We can write down, right? So if C2 has coordinates Z1, Z2 as yesterday, then omega 1 is equal to real part of dZ1, which dZ2. Omega 2 is imaginary part. Right, so these two combine into something that we could call omega 2,0 form, a complex form, and then there's omega 3, which is a 1,1 form, and that's dZ1, Z1 bar plus dZ2, which dZ2 bar. And these forms, for any such C2 mod gamma, we can construct and write these down. And one way of now sort of fibering this is to describe in very sort of rough terms the ADE. We really should be calling this ALE, but let's not go into this. So let's have the ADE fibration. We have to specify how the omega i's are fibered. Over the base. And for this Higgs bundle, phi that I was talking about earlier, we can now sort of specify, once I give you a configuration of a field phi, this will define sort of exactly these omega i's, and that will be in the following way. That so phi basically, phi, this Higgs field, reconstructs this. Or constructs basically, because we're starting really with M3 and then constructing this ALE fibration from it. So by, for example, writing, say, if we have phi is some adjoint Higgs field, so it's in some section of it's an omega 1 of M3, and it's valued in some gauge bundle, some add G perp bundle, say, or specifically, we always looked at the U1 case, so let's look at that for the moment. Actually, let me keep it with some general bundle. Because we're trying to get an ALE fibration, right, not just a U1 for the moment. And then, so phi has an expansion as a 1 form, first of all, so I can write phi I dxi, sum I equals to 1 until 3. And now each one of these phi i's will be valued in the whatever the Lie algebra G perp is, and then essentially these expansion coefficients. So this is Lie algebra valued. And so there'll be some phi I alpha dxi T alpha. And so basically what I would like to identify is these phi I alpha as exactly the integrals of the omega I forms, I is 1, 2, and 3, over some P1s, which are exactly associated to the root alpha of this ALE fibration. This is morally speaking how you should think about it. So in fact, the phi's parameterize the volumes of the P1s in the ALE fiber or in the ADE fiber. Okay. So you can think of if you specify one of these one-form fields that satisfy these Higgs bundle equations, the non-trivial vacuum expectation values for these phis parameterizes the volumes of the fibers, and as the volume goes to zero, say phi goes to zero, you're basically unhiggsing a gauge group, right? So the cycle shrinks to zero, and the gauge group locally enhances at that point. So this story actually is quite universal and general, so you might have seen this in an F-theoretic context already, or just in sort of a Hitchin. Well, actually, in the F-theory context, it's the closest to this, right? So basically, the phi field, or the expectation value of the phi field, parameterizes these volumes. And so as we move on M3, so phi is really varying, is a one form over M3. As we move about, this might actually, the volume of these cycles might shrink or might get fibered. So this is how we construct the ALE vibration.
Sorry, Sakura?
Yeah.
So these DXI are actually
these are
SU2 invariant differentials on S3, is that correct?
Sure. So here I'm doing a very local analysis, right? Absolutely. So these are local coordinates. Here I've written local coordinates on R3, but you really should be thinking in terms
to the action of SU2 on S3, since.
Sorry?
I mean, those are differentials adapted to the action of SU2 on S3,
Absolutely.
since you want to correlate it with the
Absolutely, and that happens because of the topological twist that we did, right? So the SU2, how it actually, the ALE fiber is sort of fibered over this, which is coming from some SU2 action in the 70s superannual seed, that actually is correlated with the SU2 on M3. It's very important. Otherwise, right, phi starts off as a scalar field in 7 dimensions, and now it becomes one form. And it's engineered exactly such that it will sort of make this the total space. So we can also map this actually to another description of these vibrations, which maybe I'll skip, but just to mention that you can also map this to, if you've seen these conical singularities, in Acharya Witten or Atiyah Witten's paper. By the way, I've invented a paper yesterday. It's actually not Atiyah and Maldacena and Witten, but actually Atiyah, Maldacena and Waffa. Still a nice combination. I think Maldacena and Atiyah on one paper certainly makes for a fantastic combination. Anyway, so right, if you know these conical singularities, these metrics, then the local behavior of the metric around these sort of Higgs bundle configurations actually reproduces exactly the same metric. So the Higgs bundle description is the same as the
story.
Yeah.
How did you get that the components of the Higgs field are exactly the integral of the p alphas of the Kähler forms?
So this is how I will actually identify it, right? So I told you can in this way reconstruct. You can define a local ALE vibration by identifying it in this way, right? So at the moment, we're going from the bottom up. We have M3, we have this Higgs bundle, which is solving this equation up there. And now I'm asking, in what way does this now define us actually an ALE vibration? And so one way of actually writing this is, so phi is the F, and now we can also write locally what happens where phi is 0, right? Where sort of the gauge group enhances. That locus, I can now expand F in a quadratic. So let me do this if this might be helpful, because you might have seen these singularities, right? So in fact, we can map this. Local geometry to the conical singularities. See Acharya Witten. So we said phi is the F in our case, and so around phi equals to 0, locally F, say, has an expansion, some constant, plus some sum xi squared. Yeah, so if this happens without loss of generality at x equals to 0. And now you can ask, so how can I now actually construct the ALE vibration, right? The singularity, I can now describe it exactly as Z1 squared plus Z2 squared plus Z3 squared is the sum of the xi squared, I equals to 1 until 3, in C3 times R3, right? So this is basically the local patch on M3. And so what's going on here is that for a generic point, right, generically, this is smooth, except at xi equals to, or x equals to 0, right? This fiber. So you should think of this as the C3 over R3, and the C3 now varies. So this is sort of, you view it as a vibration over the coordinates xi. At xi equals to 0, right, you get some conical thing. So actually what is happening is you fiber this over, say this is our M3, here's x equals to 0. And then what happens is that the cycles that collapse. So this actually locally looks like, what, if you've seen this before, like an Iguchi-Hansen geometry. Right, so you see these cycles collapsing wherever phi is locally 0, or for f, this is a critical point. So the critical points or phi equals to 0 loci correspond to collapse of the fiber. Okay, and this you can do not just for the simple case, but for more general AOD type singularities, so multi-centered sort of geometries. I don't think there's a sort of nice way like this for the E-type, but for the E-type we can still write down sort of this gauge theoretic story. Okay, so this is quite important, that where phi is 0, this critical loci for this function f, they're basically the loci where we expect the gauge group to be enhanced, so some cycle collapses, and so we get some additional massless modes, right? So this is sort of physically where we would expect also then matter to be localized. Okay, so this is sort of to connect this geometric picture to this Higgs bundle picture, so you know that indeed, not just sort of field theoretically, looking at this twisted Super-Yang-Mills and you reduce it, you get some gauge configuration that gives some 40n equals 1 theory, but actually that allows you to then also, if you want to, reconstruct the ADE singularity above it. That's fibered above it. Okay, but what we're really interested in are these 2 points here. How do we construct now some zero-mode spectrum and interactions? And that story has also nice mathematical incarnation, namely, what we have to do is to think in terms of now in the 70 Super-Yang-Mills, in a particular background field configuration solving the BPS equations, what are actually the zero modes for the fermions in 4 dimensions and how they're counted. They'll be counted by some particular cohomology in this space. So before we get there, we first should maybe look at what actually this twisted Super-Yang-Mills action is. This just, you take 10 Super-Yang-Mills, you put it on T3, that's 70 Super-Yang-Mills theory, and now we already have done the topological twist. That's why the fields that appear in here are already these fields written in terms of these twisted fields. So var phi is actually this combination of the Higgs field and the Wilson, or the gauge field connection along the 3 cycle. You'll see these derivatives, these straight Ds, they're just space-time covariant derivatives in 4 dimensions. And the curly Ds, there'll be covariant derivatives along M3. They will actually depend on this var phi. Right, so this is, let's see, so this curly Ds here, these are the derivatives which are actually D plus var phi wedge, rather than a mu wedge, which is what appears in the straight Ds. Okay, so let's start with this theory, and we have a background field configuration phi, so one form, and say we have, to begin with, just a U1 valued Higgs field. So we're just looking at a breaking locally or an enhancement locally from G times U1 back to G tilde. So we expect that locally what we're seeing is some sort of matter, right? So expectation is the zero modes are localized at phi equals to 0 for these representations R and with charge Q and minus Q, and there should be a bar. Okay, so from this action, the first thing that we want is what are actually the zero mode or the equations of motion for the fermions. So this curly D, I said, is basically D plus var phi wedge, where var phi is phi plus IW. As you remember, we actually chose W to be trivial for simplicity. We can also consider more complicated things where W is turned on. And then D bar, the conjugate is D minus var phi wedge. It's a bar. Cool. And so looking at from the fermions, so chi and psi, zero modes. And so we do a standard KK ansatz where there are internal components, and we just in our dimension reduce this, and the equations that they have to satisfy along the three manifold are just d bar chi is 0, d bar dagger chi is 0, and d psi 0, d bar dagger. So in fact, from here, what we find is these chi alpha, these chi fermions have to be in the d bar of M3 with whatever gauge bundle, I think I called it P U1 bundle connection, and then the psi alpha are in H1. And the form degrees, they were fixed from the twist. Yes, if you remember yesterday, we looked at these twisted, the twisted spectrum. Just 1 second, let me go back there. Right, so these chi's and psi's side bars, they had a particular transformation under this twisted group. And if we sort of propagate this through, we get this here. Maybe a more useful thing is to write everything in terms of the curly del cohomologies, and then so using sort of the Hodge duals, etc. So what we actually have to determine are the spectra chi alpha H3, D M3 P, and the psi alpha dot, so psi alpha in H1. And the conjugates are so D here is this operator, and So what we need to understand how to calculate is, so compute the cohomology, where D is a twisted differential. So for our case, where phi is equal to df, this is something like D plus df wedge. Okay, so if this f were trivial, this is a standard exercise to do. But of course, once this f is turned on, and we haven't really specified f is now some function that we now have to sort of twist the differential by and then calculate the CERN modes for that. So this is sort of not just a trivial thing to do. And remember, M3, yeah. That's right. So there's basically, you can dualize these using the phi 3. So there's the 3 form. Essentially, you can use that to dualize these forms into each other. I didn't explain this earlier. So remember that M3 is, say, S3 minus some tubular neighborhood of some graph gamma. So the boundary of M3 is some, say, sigma, which we can split into positive and negative charged components. And now the question is, well, compute these cohomologies. So the D on the space. So the first thing we have to check is that, I was very, very casual about these boundary conditions yesterday. I said, well, I can map the problem back to something that is sort of, we have phi, which is now regular, but with certain boundary conditions. And indeed, now this will sort of come back to us because we now have to, when we calculate the cohomologies, there's going to be a question, what are actually the boundary conditions along the boundary of M3? So the way to do this is use sort of some analog of some twisted Hodge complex. I don't want to sort of expand on this too much because it's more of a mathematical. There's a theorem that basically maps this cohomology to a nice cohomology that we can calculate. I want to give you some sense of this. So we want to actually determine, so by Hodge, we can map this, we can compute the twisted Laplace. So this is the delta is the Laplace for this twisted D operator, right? So Laplace F is equal to D dagger D. Compute the eigenmodes for these, so the harmonic forms for this, the twisted Laplace. And so if we write out what this twisted Laplace operator is, it looks just like, well, the standard bit, D dagger. And now, so remember here there's going to be a Q from, so really I should have written here also a Q. This is, what's important here is the sign of this charge, which will become important in the following. But so there's a Q dependence. The Q was the charge from the, Jesus. Q is the charge of R under this U1, right? So we're trying to compute the zero modes for fermions in a representation R of G with some U1 charge, which is Q, and this Q basically propagates through this thing. So this is Q plus Q squared, the F squared plus Q, and now the sum over HF, which is the Hessian of F, and then something that looks, well, I can write it in a way that looks so very nice in terms of commutator A dagger A. This here is the Hessian of F, and the AIs, they are given in terms of the simple differential operators. A dagger is just d xi, which it is just writing out what this really now means in this curly d. I've put w is 0, but phi is df, and in our case, w is set to 0. Okay, so and what we would like to do is compute these zero modes, so determine harmonic forms for this twisted Laplacian based on this space with the boundary. So now we have to actually also specify boundary condition. So in fact, key here is that so D and D dagger are actually they're not adjoint to each other unless we impose suitable boundary conditions on the forms. So if we sort of look at, say, D alpha, we have some P form, alpha and beta. Then we want this to be the same as 0 is equal to alpha negative beta. If you now evaluate this on the space of the boundary, on the boundary of M3, what this becomes is just alpha bar star beta. And so we need this to be 0. And it's useful now to sort of just decompose these forms into things that are tangent and normal to the boundary, and then impose basically Dirichlet or Neumann boundary conditions for these objects. Okay, so now decomposing alpha and beta into normal and tangent components. Right, we can now set, so this here will reduce to let's say integral the boundary of M3 alpha bar tangent wedge star beta normal. So this is normal and this is tangent components. And so now I can either impose that the tangent or the star normal components are 0, and those give us essentially two sets of boundary conditions so we can choose. And this we have to now do in a way that's consistent with some decomposition of this boundary in terms of positive and negative charged boundary components. Okay, so I will go to the next page. Just so impose boundary conditions and the forms. And so sigma, remember, was something like sigma plus, sigma minus, right? So these came from the positive or negative charge distributions. And so we can choose, for example, Dirichlet boundary conditions on sigma minus. So alpha transfers on sigma minus. A tangent is 0 on sigma minus, and Neumann boundary conditions on sigma plus. And then, with this set of boundary conditions, there's a theorem that we can show, which basically then says that this cohomology, H star of this curly D operator, M3 with this particular U1 bundle, then just reduces to something that's actually nice and computable, which is just the relative cohomology of M3 with respect to negative boundary. And so at this point you will say, oh, why is there now an asymmetry between the negative and the positive boundary? So this, of course, comes from the particular choice of how we've picked this charge. So if, for example, Q goes to minus Q, then sigma minus swaps with sigma plus. So this is just sort of, right, the total charge is 0, and somehow by picking this particular set of conditions, you pick out this the cohomology with respect to the negative boundary. Right, so this is the relative cohomology Okay, so in fact, this already now gives me a way of calculating, given, say, a sphere with some charge distribution, positive and negative charges, you ensure that the integral of the full charge density vanishes. And then, for example, for point charges, we could write down this immediately, what the cohomology is for this. There's actually, maybe I will do this before heading to, yeah. Let me just, I would like to give you at least this formula for, this I can evaluate for, say, a sphere with a particular set of boundary components. And then literally the counting of their modes just comes down to some combinatorial thing. How many boundary components are there of a given charge, and how many connected components, are they loops or not, are they interlinked or not, something of this type, yes?
In terms of intersecting branes in the type 2A picture, can I think of these charges as incoming branes, right?
Absolutely,
And
yes.
the plus minus is the relative orientation.
Yeah, absolutely. It's just that you don't always have a type 2A picture.
Sure, of course.
The local geometry,
of course.
the local geometry on M3, right? So this is very important. So the phi actually is a section of T star M3. So you get a local Calabi R3, but this is not the local G2 manifold, right? But you could, in the case of an A type, indeed go to a type 2A description, and then exactly this was that. We would do that.
So if it's point-like, then there's a relative orientation, which is plus and minus. And if it's real dimension 1, the charge contribution, isn't it then both plus and minus at the same time? Because there's no orientation? I'm confused.
So it is actually plus and minus is, so you're asking, oh, for the charge distribution?
Yeah, so if you have two, if I'm allowed to think in type 2A for a second, if I have two special Lagrangians intersecting on a real dimension 1 sublocus.
But this is the charges are not the loci where they intersect, right? So the gauge enhancement happens at higher loci. Right, this is at the point. So phi equals to 0 is the locus where you actually have the gauge enhancement.
Yes.
Right? The charge distribution is not, right, where gamma is not where phi is 0.
So right? what is then the charge distribution in the intersecting brane picture?
So this depends. Right? I will write down actually examples. I will tell you now, this we can evaluate for given S3 with some loops and links and whatever, and then actually determine what that relative cohomology is. So you don't even need to calculate where is now this phi equals to 0 locus. But so what is, however, important, and this is a point that we'll get to maybe a bit later, is phi here, right, can have, I haven't said anything about it, where phi actually has these lows. It could be dimension 1, it could be high dimensions, and depending on that, there might be a slight difference in the description. But this cohomological formula holds true for, I haven't made any assumptions about are these isolated critical points or not, right? So if you now map this actually to this Morse picture, which I might not have time to get to, but if the critical points are isolated, then you are in the case with a Morse function. If they are not isolated, then you're in the case when you have Morse-Bott functions. F is a Morse-Bott function, but still, you can still apply this. This expression is still true. Right? If you can calculate this, you can actually extract the cohomology in this way. It's just that other picture is useful to then get the couplings. Anyway, so let's look at this for the specific case for S3. So the example, right, so you have S3. And gamma is a collection of, well, it can be, it's just a charge, it's the support of the charge distribution. So this could be links or points. So if we start describing what this is, so n plus minus, say, is the number of components, plus minus charge. L plus minus is the number of loops. And then we also need a sense of when I have plus and minus charges interlinking, that sort of, the measure of that is the number of minus loops that are independent in homology in S3 minus gamma plus. Right, so I take out the gamma plus and I ask how many negative loops I still have in that space. And then actually this relative cohomology, so the H, so here this P should be a star, obviously. So, yeah. On M3 with respect to gamma minus or sigma minus is then just given in terms of the B1. Yeah, let me be. So this really is sigma minus, right? So it's a little annoying thing that, so I'm extracting out the tubular neighborhood and the boundary of M3 is sigma. Right? It's not gamma because it's a tubular neighborhood. So M3 with sigma minus is then just the number of loops with positive minus n minus R minus 1, and B2 of M3 sigma minus is L minus plus n plus minus R minus 1. So this is using basically chasing some Meyer-Viatori sequence. This is a sort of, in S3, a relatively simple way to characterize this. Now, and so the chiral index is now just going to be n plus minus L plus minus n minus minus L minus. Okay? So it only depends on essentially the difference of n plus and the n plus minus L plus minus, whether you have an offset of chiral or versus anti-chiral representations. And this is all for the case for U1 phi, and phi is this df with all the bells and whistles that we described. Okay, so for example, really a trivial example, point charges, say plus, minus, minus. There are two critical points here. And so the L plus minus is 0, but the N plus is 3, and minus is 2, so chi is equal to 1, unequal to 0. It's about as trivial as that. Of course, you can do much more interesting things with loops and links to get something chiral, but certainly this is a pretty simple characterization, at least on S3, of how we can get some matter with a non-trivial chiral index. Okay, so I would like to, yeah. Yes.
Then the chiral matter is at points. This example, which I just had.
Okay. These points are not where phi is equal to 0.
But these are these n plus equals 3 and n minus equal 2, no?
No, these are the charges, right? So the problem is you're solving for Laplace, f is rho. Now you're just taking it out from the manifold, right, and so on. And now basically where phi is equal to 0 are the critical points of f. So those are the points, these points that are marked in the middle, right? These are these points here. These are the critical points. I mean, morally speaking, they're here, right? The charge distribution is fixed. Maybe I shouldn't have done point charges. You can do loops, right? So you have a loop, another loop, and then there's I will show you probably in the next lecture, in the case of this twisted connected sum, how it looks like. It's, for example, concentric circles. You have a circle, another circle, and there's a critical one-dimensional thing, and that's where phi is 0. Okay. So in the last 5 minutes, it's a real shame because we spent so much time explaining this. So there's a beautiful way of understanding this using supersymmetric quantum mechanics, which I won't get to. But so why is that important? It's because, well, we went through this. Where is it? Where's the Laplace? Here. So this Laplacian already looks kind of similar to something, right, which you might have seen before. So you can think of this, and this is a classic story in a paper by Witten on quantum mechanics and Morse theory, and you can describe essentially the cohomology of these harmonic forms that we're trying to compute here in terms of quantum mechanics, well, the target space, supersymmetric quantum mechanics with a target space, the three-manifold M3. And so let me just maybe sort of tell you briefly what the idea is for that, and then why this is sort of important. So there's an alternative description of the zero modes is in terms of superquantum mechanics and the associated Morse theory. So the Witten paper of that title, or there's a beautiful overview in the book by Mirror Symmetry book by Hori, Katz, and many others. So the idea there is that we're thinking of our D and the dagger operators basically as supersymmetries in a quantum mechanical theory. F will play the role of a superpotential, And the zero modes, i.e. the things that are the harmonic forms, they're the ground states for this quantum mechanical system. And this basically amounts to a super quantum mechanics, which is arising from this Laplacian nabla F that I had written down, which is basically close to a critical point i.e. df is equal to 0, i.e. right, well, f is equal to, so phi is equal to 0, close to a critical point. So f has an expansion as some constant plus, say, a quadratic piece. This just looks like minus df d by xi squared plus q squared c I squared xi squared plus q ci. Right, this is just looking at sort of applying delta f from before to this specific expansion around the critical point. And these CIs are just the, if you remember, there's the Hessian that appears there. So the I's are just, the CIs are just the evals of the Hessian. So really the sign of these is important, and that appears in this last term. Okay, and now the critical points, so a function, so at this point we sort of need to make an assumption. We would like to have this to be a function that has an isolated critical point. So the critical locus is sort of a point that's isolated, sort of family of loci, and at that point we have this expansion. So here we make an assumption. Here, assume f has isolated critical points. In fact, f is what is called a Morse function then. If not, if non-isolated, then f is Morse bot, and a similar thing as what I'll describe will apply. It's just that it's a little bit more complicated, but it will be relevant for the G2 manifolds that we will discuss in the next lecture. Okay, so now basically this object here, I can now, in fact, let me just add one more thing about these Morse functions, right? And so the critical points of f are characterized by the CI. So essentially, we can define for a point P something called the Morse index, which is just the number of evals Ci of the Hessian of f at the point P, such that Ci is less than 0. It's the Morse index. So you think of there's some function, right, and then it has some saddle point, and then you would say, well, there's sort of a plus, and there's a minus, and so this has basically Morse index 1. And sort of just a brief summary, and I might actually put a more expanded version of that into the notes that I'll upload on the CERN webpage with these lectures. So brief summary is that the zero modes for psi and chi, they're going to be essentially in this quantum mechanical system with the Hamiltonian. Yes, did I say this? Oh, I didn't say this. So of course, if these are the supersymmetries, right, the delta F will be Hamiltonian. Yes, and it's quadratic, so it's something we all know how to solve, right? So I said these are the SUSIs, so the Hamiltonian will be exactly this twisted Laplacian. If I identify these, then these are going to be wave functions in this quantum mechanical system, and in fact, the ones which have Morse index 1 are going to be the psis, and these are 1 forms. These are 1 forms. And Morse index 2 are the bars which are 2 forms. Anyway, these are perturbative states, and then there's sort of an important correction to this picture. You're looking at the quantum mechanics with quadratic potentials, a harmonic oscillator, but there will be instanton corrections to this problem, and these instanton corrections then will really, once the dust settles, will sort of say some of these ground states are actually not there. There's sort of some tunneling between these two. So some of them disappear from the spectrum. And in the end, what it will do, just really completely cutting to the end because I'm running out of time. At the end, what this generates is exactly this cohomology that we found here in the case for this quantum mechanical system. I might expand on this a bit more because to explain actually couplings, I will have to describe to you at least how this story will reconstruct this ALE vibration. So maybe we'll continue there in the afternoon. Yeah, but anyway, I would have liked to have gotten through that before, but it is what it is. Okay, other questions? Yes?
Yes, so you counted the zero modes in a fixed background of the fixed charge distribution that gives you some chiral matter, but I presume there are also massless degrees of freedom associated to the choice of charge distribution, right? The location of these points on the sphere, or maybe the shape of these links. Is that
no?
Are those moduli of the G2 manifold that you reconstruct?
Yes, but it doesn't, right? So it's literally, it doesn't seem to depend on this at all. It's right, so you could have two loops and they interlink, and you can deform them a little bit. And in fact, I will give a nice example in the afternoon. So, but let me tell you the example. So take.
So the chiral spectrum does not depend on these deformations.
It doesn't depend on the deformations as long as you don't change this data.
Yeah, sure.
The loops, the interlinkings, and so on. So, for example, in these geometries that we'll discuss later, you have concentric circular, two concentric circular charges. So the critical locus is a one-dimensional thing if they're concentric. Now, you deform them a little bit, you make them elliptic, but still concentric. Then the critical loci will now be points. But still, this doesn't change, this doesn't actually affect the spectrum. The chiral index is not affected.
Sure, but still the deformations of this charge distribution are moduli, geometric moduli of this.
Absolutely, yes.
But it looks like there are infinite number of possible deformations if you have this.
Yes, so this is a local statement, right? This is a statement about if you are close to a locus where there is a singular ALE fiber above this, then you can describe it in this way. So in the TCS, for example, in these compact geometries, these are not infinitely many moduli, right? You're restricted by what you can actually do by staying within this class of geometry.
Some global obstructions.
That's right. So, right, but this we know, this also in F theory, It was never the case that you could do anything that in this local model is a deformation will lift to a global model. But it gives you a pretty good idea of how you can engineer certain things and what certain deformations, what effect they have. So in fact, what I would do is use this sort of argument to say, how do we need to modify these compact global model constructions to actually get something that has chiral matter in a compact model? I won't construct for you the G2 metric on these things, but I tell you how do you need to modify it to get that. Because I sort of extract exactly this data from these compact geometries that we know, and then say, these are not good because they're non-chiral. But I can tell you what you have to do in principle, and it will be going beyond the types of geometries that people have constructed, but it will be a very specific, concrete proposal of what you have to do to these things. They are moduli, but they're kind of, from the physics, they're uninteresting moduli, right? From the point of view of a chiral index, they're uninteresting. Yeah. Any other questions? Yeah, absolutely, sure. So I will continue with, actually, just so you know what you will get in the afternoon is, I will do some more of this. I will actually maybe write it down, so it explains sort of to you briefly the logic behind the superquantum mechanics, because that's important to then actually get the couplings, Yukawa couplings. And then I want to discuss some of the compact geometries that are known. Okay, see you there.